Hi, am I audible? Am I audible? Let's wait for 1 minute. So if you have any questions regarding previous classes, yeah, you can ask. Okay, just a minute. Just a minute. I opened the discussion forum, right? Yeah, yeah. You asked some questions and some of things are replied, right? Yeah. So further, any questions? Yes. Tell me. Yeah, P versus PP graph. Yes. Yeah. So the thing is that if you always say that in the lectures or as well that we have plotted x versus y, right? So then have p in the x-axis and pv in the y-axis. Yeah. No. Yeah. Yes. Yeah. Okay. So just a minute. So, and which assignments? Assignment 6 or 7? Yeah. Yes. Okay, just a minute. Yeah. Assignment 6, question 5, right? Yeah, so then if you choose the P in the x-axis and PV in the y-axis, then this is a horizontal straight line. Otherwise, the opposite condition gives the horizontal vertical straight line, right? So yeah, but there is a little confusion. Okay, so the thing is that so yeah, yeah, so yeah. Yeah, but the thing is that all the assignments are based on the lectures, right? So if you watch the lectures and then you can know that which in the y. The convention somehow is not stated properly in the questions, but they follow from the assignment, classroom problems. Okay? So, but again, still a problem. But I think these types of issue corrected at the end. I think there is no problem. But you understand the so you understand the, it's just a confusions of this or maybe there is some So basically at the end, I think that these questions are not graded. Actually ruled out. Right? There are many problems. There are many questions. There are typo, right? And you already mentioned, and some of the other students also mentioned. So these questions I think not considered for the grading. Okay? So don't worry about this. Understand? Yeah. Assignment 3, question number 1. Yes. Yes. Yeah. 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 Absolutely not, but there is multiple things. Right? So the viscosity is the independent of the pressure at the moderate pressure and temperature. Right? Yes. Yes. So according to things that B and D both are correct, but this is this is a single option correct option. That's why the accepted answer is only one soon, but it will be corrected at the end. So I think it will go down. So you understand the thing that is most important, but those there are many typos and problems in the questions. Okay, so I think at the end all of these questions are considered for, not considered for the game. So yeah. Or any questions? Assignment 6. So, yes, yes, van der Waals. Yeah, due to the van der Waals correction, the pressure exerted by the gas compared to an ideal gas will answer it quickly. No, no. What is happening is that when we consider a real gas, right? Then due to these attractions, okay, so the pressure decreases, right? But we write a equations of states such that we actually pointed that where this decreases actually comes into the picture. So that's why we write P plus A by V square. So that A by V square actually decreases, but we compensated theoretically that in the equations of state, written in the equations of state in such a way that we mentioned that the things will be decreases due to these attractions of the molecules. So due to this van der Waals correction, the pressure exerted by the gas compared to the ideal gas will be decreases. Yeah. Oh, this will be uh, assignment 6. Yeah, I think there is some problem in the assignment 5 as well, right? So if you calculate for ideal gas and real gas pressure and there, and write down the ratio. Yeah, that is true. That's why I'm saying, right? So if you allow attractions, then interactions of these molecules, the pressure will be decreases because the less molecule hit to the walls, right? So right. So okay, yeah. So again, this is a problem. So you raise these questions in the discussion forum, right? Okay, I will mention that there is a typo of this. Okay, okay, so I will reply those things. Or any questions? Hey, yeah, yeah. About the, yes. So I refer to YouTube link, right? One of this. Yes, yes, right. Yes, wait. No, no, no. Yeah, yeah. Accepted. Okay, okay. Let me bring out my screen. Okay. My screen is visible now, right? My screen is visible now. Okay. Yes, yeah, right. Yeah. So when we increase the temperatures, okay. So then you calculate the maximum probability, maximum probable velocity MP VMP, right? So this will depends on the square root of t. So when we increases the temperatures, so when we increase the temperatures, when we increase the temperature, this maximum probability velocity increases, right? So that means this point shifted to this point. Okay. So at higher temperature, let's say T2 is greater than T1. And if you calculate VF of VMP, that means the value of this function f of v at this point. Okay. So they follow these distributions a VMP square into e to the power minus alpha VMP square. So when we calculate at VMP, so then we get that 1 over t to the power half, right? So that means temperature increases. Since f of VMP means that at this point this value. So f of VMP at temperature T1, this value, and at higher temperatures this must be decreases. Okay. So that means your height decreases, and the velocity, the maximum probable velocity also shifted. Okay. Yeah. So now there one more condition is that the normalizations, that 0 to infinity f of v dq v is 1, right? So then that if your area is preserved, okay, under the curve, right? So this must be broadness, right? The curve must be broadness. Okay, otherwise the area not preserved. So if your curve is sharp, if you want to your area preserved with these properties that the peak point shifted and decreases, so that your curve must be broadness. Okay. So the normalization condition tells that this thing must be happening because your area under the curve preserved. Okay. Yeah, it's clear now, right? Okay. So yeah. So these questions actually there are 12 week 12 assignments. So I think the 11 assignments will be counted, and so all of these questions are errors or there is some confusions regarding the statement of the question. So these questions are not getting. So any further questions that you have a doubt? Okay, so uh, today I will discuss briefly about some heat engines and calculate the efficiency, or then we go into that and do some problems related to the heat engines and second law of thermodynamics. Okay, so by the way, you are easily accessible to all the recorded video and the lecture notes, the live. Okay, it's protected, right? Password protected, or if there are kind of permissions needed, right? Okay, okay. I will inform this thing. Okay, to the, okay, okay. I think this is not public yet. Okay, these things I will be noted and I will inform. So, uh, okay, so far we learned about any other questions related to the assignments or things. Okay. So you posted the discussion forum as well. I will reply the team member. So far we learned about the basic concept of the heat engines. So what is the heat engines that? So heat engine which are a machine. Uh, so so which are machines that produce work from produce, work from a temperature difference between two reservoirs. So between So this is a very important thing that when we consider talking about the heat engine, that means they are operate always the two different temperatures, right? So that means to reservoir, the concept of reservoir, I think you know that. What is the reservoir? That if you suck some heat from there and put some heat, there is no change in the temperature, right? So if always there is a two different temperature and we working and we put engines between the heat engines is always working with the two different temperatures. Because schematically we write that schematically schematically means that there is a reservoir, let's say at high temperature pH, and we operates the heat engines. So other kind of engines I am talking about just in few minutes, that they are not operates in that two different temperatures. Okay. So the heat engine only operates to different temperatures, TH and TS. So this is a high temperature and low temperature reservoirs, and the heat engine operates um, uh, that things that the temperature difference between the two and produces some work done. So this engine, I am saying that this E, okay, so this heat engine can be a real engine or a Carnot engine. So real engine. So let's first consider the Carnot engines. So if this engine is a Carnot engine, so Carnot engine is a heat engine, is a special heat engine that follow the two reversible isotherms and two reversible adiabatic processes. So this eta Carnot is a W by Q in, and the total work done by total heat input, that is the efficiency. This is the efficiency, and if you know that this is 1 over TL by TH. So this is one type of heat engine, and all reversible other heat engines are the same efficiency as the Carnot efficiency. This is the Carnot theorem. In the previous class we discussed. Now, if this heat engine is real engines, this is not a reversible. So then there might be if this heat engine is not a reversible engines. So one of the example is the Stirling engines. So the real engine, so this heat engine might be a Carnot engine or a real engine. So Carnot engine is a reversible engine and this is a real engine. So this real engine, the one example is a Stirling engine. So these are the real engines, and in these real engines, the efficiency of this real engine is always less than equals to the Carnot engines. Efficiency of the real engine is always less Carnot engine. So and what is the problem with this different type of heat engines? The problem is that the such an engine literally has to warm up to establish the temperature difference, and so it is harder to regulate the power out. So first we difference the temperature difference between. So when we operate the heat engine, we need some two reservoirs at different temperatures. Right? So we need a temperature difference. We need to create first a temperature difference reservoirs, and then we operate the heat engines. Right? So the problem is that it is harder to regulate a power output. So when we, let's say we power output means in this case is the work done, right? So if you have to regulate the work done for different work done, right? So that means we have to change this TH and TL, right? So a reservoir temperature you have to change, and this is a harder to but a complicated task to changing this to fixed temperatures in order to produce a work done to regulate. So that's why the internal combustion engine, which is the internal combustion engine, is that the diesel engine or petrol engine, right? So this is not a heat engine. So the internal that's why we need a internal combustion engine. So this engine is the diesel engine. Diesel engine, petrol engine. Okay. So this kind of engine. So in this case, that the burning of the fuel inside the engine's combustion chamber generates the high temperature and pressure necessary to use fuel. So and easy to operate, that we want to change the fuel and we produce a more work done, or and easy to regulate this kind of diesel engines, okay, rather than the heat engines. So if we written explicitly that the burning of the fuel inside the engine, inside the engine combustion chamber, the engine combustion chamber generates the high temperature, generates the high temperature and pressure necessary to use for necessary, necessary to use for work, and that's why these types of engine used in most automobile applications, okay. So this is easy to regulate the power, easy to regulate the power output, okay. uh, Unlike the heat engines, unlike heat engine, that's why that's why this type of engine, this type of engines used in most automobile applications. So regulate the easy to regulate the power supply, unlike heat engines. Okay, this is clear that why we need this diesel engine and what is the most important of this. Okay, and what is the difference between the heat engines, okay, and diesel engines. Yeah, you doubt. Okay. So, so what kind of then? So, as I say that the engine is always is a cyclic process, right? Because in order to produce a steady power, we need a cyclic process that operates more and more, and to at the end we produce a steady power, right? So that is the engine. So it's always a cyclic process, but may not be reversible. May not be reversible, right? So if this is a reversible engine, then reversible heat engine, this is a Carnot engine, the same efficiency, and is it not a reversible, not reversible, that means the irreversible engine, that is the real engine. But the engines always the cyclics. So then let's do one example of this internal combustion engine, like a diesel engine, that is the standard Otto cycle. So this Otto cycle. So these cycles also discussed in the class. So this PV diagram is just like contents of two adiabates and two isochoric processes, right? So this process, let's say this. So this is a adiabatic, this is also adiabatic, and this is a isochoric. So right. Let's just consider one, two, three, four, and they are same volumes. So that means V2 equals to V3, V1 equals to V4, Then we want to calculate the efficiency of this standard order cycle. Right? So how to calculate the so we know first to calculate the work done, the net work done, net work done. So this is just a, so in which process the heat input and in which process the heat out, can you tell me just heat in and heat out in which process? So adiabatic process there is no change of it, right? So that means in this process that dq equals to 0. The heat is in this process the heat is a q, let's say 1, and in this process the heat out, let's say q. Okay. Or using this notation that ql and qh. So qh is in and ql is out. Then the net work done is that that close this our cycle, this PTB, and integrate over the whole cycle. So in this process the dq is 0, 3 to 4 process, and 4 to 1 is QL, and 1 to 2 again 0, and 2 to 3 QH. So this is a QH minus QL. This is the net work done. Now we write down the QL and QH in terms of the temperature difference. So we write down the QL, which leaves, so that's a minus sign, MC T1 minus T4, right? And QH, it enter plus sign MC T3 minus T2, the temperature difference. So because that delta Q is MC delta T. Right? So C is the heat capacity and M is the mass of this working substance. So M is just the mass of the working substance, and C is the heat capacity. Right? Then what the total heat input Q in QH. So the efficiency is that W by QH. So it's 1 minus T4 minus T1 by T3 minus T2. Right. And we just simply calculate that 1 and 2 are connected, and 3 and 4 are the adiabatic process. So then they connected this, so T4 by T3, T3 by V4 to the power gamma minus 1, because we know that the T v to the power gamma minus 1, T v to the power gamma minus 1 equals to constants. We are considering ideal gas. So this is most important that we are considering ideal gas. PV equals to, let's say, KT, or PV equals to RT. PV equals to RT, and the adiabatic process. So P to the power gamma equals to constant, and we replace this P in terms of temperature T, these equations of states. We end up with that T to the power gamma minus 1 equals to constant. Right. So at each point the equations of state must hold, right? So in this point the pressure is P3. So in this point the pressure is P3, volume is V3. In this the pressure P3, volume V3. This means RT3, the temperature. Right. In this point pressure. So at each point, every point of this Carnot cycle, or every point of this cyclic process, the equations of state must hold, right? And in this point that P4, RT4, right? So now these 3 and 4 are connected through this adiabatic process, right? Adiabatic curve. So that means that T4 and T3 must be equals to V3 and V4 to the power gamma minus 1, right? Similarly for 1, 2, similarly for this process and this 1, 2, this adiabatic process, they are connected the T1 by T2 is V2 by V1 divided by gamma minus 1. So now we know that this isochoric process tells that the V1 equals to V4, and V2 equals to V3. Just put into this, we get that T1 by T2 is actually T4 by T3. Okay, and this algebraic relation tells that this T1 minus T4 is equals to T2 minus T3. And which is equals to V2 minus V1 to the power gamma minus 1, because V3, V4 are just related to the V1, V2. So then your efficiency eta is 1 minus V2 by V1 and gamma minus 1. So we can write this in terms of that 1 by R to the power 1 minus gamma. Right. So sorry, can write this eta using this. So where R and gamma is just a Cp by Cv, the ratio of this is the adiabatic index, the gamma, and they depend on the gas. So if you consider a monatomic gas or diatomic gas, this changes the gamma. So this is the adiabatic index. And this R, where R is the compression ratio. R equal to V1 by V2. Because we compress that V1 to, so V1 is higher, right? So in this case, the V1 is the higher volume and V2 is the lower volume. So you have to compress this V1 to V2 through the process 1 to 2. Okay, through the process 1 to 2, you compress the volume V1 to V2. So we denote that this R, define the R is a compression ratio, that is V1 by V2, and the efficiency depends on this compression ratio, right? So in the standard Otto cycle, so you have to plot this this eta, the efficiency versus this compression ratio R for different gases. So let's say consider these, and these. Yes. So this is for the exhaust gas. Let's say gamma is 1.30. This is, let's say, for air. For air, this gamma is 1.40, and in this case, the monatomic gas. This is monatomic gas. So gamma for monatomic gas. What is the values of gamma? A monatomic gas. Okay, so you know that the gamma is 1 plus 2 by F, right? Yeah, 5 by 3. That means 1.67, right? 3 2, yeah. So just for monatomic gas, F is 3, so 1 plus 2 by 3, so is 5 by 3. So F is the number of degree of freedom. So answer know this for ideal gas. Just yeah. So the main point of this that after certain values of this compression ratio, all the graph for exhaust gas, air, and monatomic gas are asymptotically flat. All the graphs are asymptotically flat. That means the efficiency does not depend on this compression ratio after certain limits. So for a given For a given diesel and petrol engines, this compression ratio restricted to some maximum value. So let's write this properly, that beyond certain value of the compression ratio, certain values, you have to just plot in the plotting software. You just plot this 1 by r to the power 1 minus gamma and put the different values of gamma. Okay, and plot this eta versus r, and you see that this kind of graphs. And this beyond the certain values of the compression ratio r, okay, so the increases in the thermal efficiency is very small and it almost flat. The increases the eta almost flat beyond certain values of this r. So which implies that for a given diesel engines, so this is standard. This standard Otto cycle is a part of the diesel engines. So the internal combustion engine, diesel engine, and the standard Otto cycle is part of this. So for a given diesel engine, this compression ratio restricted to some maximum value. Ratio are restricted to some maximum value. So you cannot compress in arbitrary. So there is some restrictions. So you have to do that because otherwise, if we compress more to produce a more quark or some other things, you cannot change the efficiency, right? So that's things that are wanted to tell. And okay, so far any questions? So now we are considering another cycles. So for a some engines, let's say the PV, I consider this cycle that E point A point to B point, they are connected to the adiabatic process, and B2 so A to B connected through the adiabatic process, B to C connected through the isobaric process, pressure constant, and C to A connected through the isochoric process, the PV plane, right? So in this case, that the adiabatic process dq is 0, so heat must in through this process QH, and in this process it reflects QL, right? So let's say P1, this point P2, this is P1, this point is P2. So now we calculate the efficiency of this cycle. So first we calculate the net quark done. The efficiency is that the eta is net quark done W by QN. Okay. So that is the definition of the efficiency. So first we calculate the work done, net work done. So the net work done, W plus this PdV. Over the cycle, I calculating the PdV because dW is PdV, and we integrate over the cycle this PdV. So for this process A to B, A to B PDB plus B to C PDB plus C to A. Again goes back to the cyclic process. So C to A, so again back to A as PDB. So can you tell me that what is this? This quantity gives that C to A PDB. C to A, it means this process. This process is that isochronic. Sorry, yes, isochronic. What is this integral value C to A PDB in the isochronic process? Yes, because the volume is does not change, right? Volume constants. So in this process, B to C PDB is just a pressure constant P1. So P1 times V1 minus V2, right? So why we write V1 minus V2 and V2 minus V1? Yes. Okay. And now next we calculate this PDB, right? So A to B PDB. So this is a from A to B, this is adiabatic process, right? So we calculate for the adiabatic process, the work done for the adiabatic process, which gives for ideal gas. Again, we consider ideal gas and calculate the work done for the adiabatic process. Which gives that, this state is that the P1. So this is let's say P1, this is P2. So that means this is P2. So this point P1 V1 at T1, this point P2 V2 at T2. They connected adiabatic process. Now we calculate the work done for this process. So how to calculate? We just put that P V to the power gamma equals to constant, some constant, let's say C, and then we replace this P in terms of this constant C by to the power gamma and calculate this integral. So we get that the P1 V1 minus P2 V2 by gamma minus 1. We calculate previously. Just go back and check. Just a simple integration. So that means the total work done W total is yes, the total work done W is that the P1 V1 minus P2 V2 by gamma minus 1 plus P2 times P1 minus V2. Next, we calculate the total heat input Q in. Yeah. So for Q in, so heat input this in this process C to A, and at A point the temperature is T1. What is the temperature at this C point? This is not T2, right? So this, let's say this the T3. At this point, point, the temperature T3. So if you know that, you know that the dq just m c dt. So the temperature difference, and m is the mass of the working substance, and c is the heat capacity. So then is that gives that m c T1 minus T3. So Q in. T1 minus T3. T1 is higher, and so T1 minus T3. So I denote the same notation QH. So now for ideal gas, what is this? So now C, but in this case that the heat capacity at constant volume, because the A2C process, the volume is constant, right? So that's why the C heat capacity is replaced by the Cp. Okay. So then for ideal gas, what is the Cp for ideal gas? For ideal gas, the Cp, if you calculate, that is R by gamma minus 1. Okay. So it's just a dq by dt at constant volume. The definitions of the Cp is that dq by dt at constant volume. If you consider this mass of the working substance, consider this a mass of the working substance embedded in the sea. So then this is R by gamma minus 1, T1 minus T3, and if we replace this T1 in terms of so RT1, what is the RT1? RT1 is the P1 P1, high equation substrate. What is the RT3? This point P2 P1 equals to RT3, right? Because in this point the V1 and P2 pressure is P2. Okay. So P2 V1 equals to RT3 in this point, the equation substrate. Because we are denoting the temperature T. Then this RT3 is that the P2 V1 by gamma minus 1. So that means this Q that V1 times P1 minus P2 by gamma minus 1. Okay. Now we can put into the formula that eta is W by QH. So what I get? Yeah. So then just a little algebraic manipulations. So P1 P1 minus P2 V2 plus P2 V2 minus P2 V1 plus gamma into P2 minus V1 times P2 divided by P1 minus P2 times P1. So this P2 V2 cancel, and so you replace that with 1 minus gamma into P2 minus V1 divided by P1 minus P2. That is the 8. So if you write in the more compact form, this eta is 1 minus gamma times P2 minus V1 minus 1 by V1 by V2 minus 1. That is the efficiency of this Carnot cycle. In the same way, we calculate in every cycle, not a Carnot cycle, of this cycles, of this particular cycles. So in the same way, you calculate the efficiency for any cycles. So the two things, one is that which have the what is the process of the cycles, and which gas are considered. So if you consider the ideal gas, and so then use the ideal gas property, PV equals to RT, and then connect the if they're connected to the adiabatic process, then we use adiabatic relations, right? And calculate the total work done and total heat input separately, and just put into the efficiency formula, we get it. So you calculate in the more complicated cycle, just following the steps. Right? Okay, so up to this point, any questions? Yes. Yes. Okay. Uh, which lectures? Can you tell me? Yes, so that's why I'm asking which week 8, right? Yes, in week 8. Just a minute. So, process lessons. Which page? Can you tell me the page number? Yes, Clausius lessons. Yeah. Yeah. Why if I consider the negative side, reversible and 37 and 32. Yeah. Yes. Okay. I will discuss this. Okay. So let's discuss briefly. Let's consider a cannot cycle and let's say and so in this case we have been enter QH and also QL, right? So so you know that this QH by QL is related to the TH by TL. Because this is isothermal process. They have some temperature TH and TL, right? So this is so now we define that. Let's say we calculate the over the whole cycle. So calculate this delta Q reversible by T. So in the first 1 to 2, delta Q reversible by T is that the QH by TH, because this is a heat enter, that's why we take a positives, minus, so this is expansions 1 to 2. Now 2 to 3, delta Q 0, right? And 3 to 2, 3 to 4, yeah, 3 to 4, the QL is leaves and we have compressed the gas. That's why we say that the QL by TL, right? And then 4 to 1 again 0. So this quantity, this relation tells that this quantity is 0 for a reversible process. So that is the sign conventions. Yeah, so in the standard conventions, yeah, so if we not that q2 is negative actually embedded in this q2. Okay, because we know that the q2 is always out, so that the q2 is a negative. So let's say we say so if we write in this way that q1 by t1 plus q2 by t2 equals to 0, that means when we hit enter, that means you say that the q1 is plus 100 joule and q2 is minus 50 joule, because q2 is leaves. So you absorb the minus sign in the q2. You understand my point? Uh, you, the standard is that several books written in the several ways, right? So if you write the q1 by t1 minus q2 by t2, that means you say that the q2 is leaves and the minus sign, that's why. If you take a plus sign, then you absorb the minus sign in the q2. So when you consider the heat leaves the q2, that means q2 is a minus 52. Yeah. So because the heat leaves is, so when we put into that the 100 joule are input and 50 joule are out, right? So that means you say that the QA is plus 100 and QL, that means the Q2 is minus 50, right? So it's already there is a minus. That is the thing. So the when you calculate the thermodynamic process like this, the work done, heat, is always the sign convention is most important. So which sign you con, otherwise you got a different answers. Okay, and the several books are written in the several way, and the convention are, so you must follow one conventions throughout this calculation. So that means that, so now start from this, so that you ask this. Okay. So, that means that for a reversible process, this dq reversible by t is 0. For any reversible process, this is 0. So that is the definitions of the entropy. Right? For irreversible process, if you just discuss in the class notes, okay, so just follow that. For a irreversible process, the irreversible process, this irreversible process, this dq by t is always less than 0. Irreversible process, it's always less than 0. Therefore, the Clausius theorem that for any closed cycle, Clausius, for any closed cycles, closed cycle is dq by t is less than equal to 0. If this cycle reversible, then the equality sign holds, and if this cycle is not reversible, then this less than 0. So the equality holds only for the reversible cycle. Equality holds only for the reversible cycle. Okay, good. So next, yeah, so from this point, so we know that for a reversible process is dq by reversible t gives a 0. It means that the integral, what it means that is dq reversible by t, it gives 0 for a reversible process. So it means that the integral, let's say a to b dq reversible by t is path independent. Right? Because you can know that there's this point. So if you connected this path, right, I can consider any path, and close this path, and we know that the over a closed cycle this is 0. That means we consider this path and this path whatever, but it keeps it the same value. Right? So let's say A path and this is a B path. So we calculate through the A path this dq by t is actually the minus of this B path dq by t. So it does not depend on the path. So calculating A path or in calculating the B path, no, this is not a minus sign because the integrate the limits the compensated for this minus sign. So 1 to 2 and 2 to 1. So if you take that, so both are limit 1 to 2, then this minus sign is compensated. Understand? So this path A through this path. So this integral is independent of the path. Right? So this is actually more specifically is actually minus sign. This gives a minus sign, but the integral limit is 2 to 1. And you know that this 2 to 1 will be plus 1 to 2, so the plus sign. So this is a path independent. This is a path. So and then that's why this quantity is a exact differentials. So when the quantity is that the indicate of this quantity is a path independent, that means this quantity is exact differentials, and it's always we in the previous class already discussed that any exact quantities or any exact differentials quantities are always state variables, right? And from this, that's why we define the entropy, which is state variable that dq reversible by t. Very important point. The dq reversible is not a path independent. Okay. So that's why this is not a state variable. But dq by t is a state variable because this dq by t is a exact differential, right? So that means the dq reversible is not exact differential, not exact differential, right? But dq by t, so that's why this is not a function of state. So this is not a state function. So this is not a state function. But if we divide it by or multiply by 1 over t, so these inexact differentials become an exact differentials, and that's why there's some kind of state functions that is called the entropy. So this is a defined. This is a entropy. So that means for adiabatic process, dq reversible is 0, right? So this implies that entropy must be constant. So for adiabatic process, entropy must be constant, and this is called the isentropic process. So adiabatic process is also called the isentropic process. So why there is a two name, isentropic process and adiabatic process? And entropy is also constant because then we are considering in the TS plane, the conjugate of the PV plane. So if you draw a PV plane diagram, so the Carnot cycle, let's say. So if you go into the TS plane, the entropy and this plane. So first this process 1, 2, 3, 4. 1 to 2 temperature is constant. So in this process, the adiabatic process in the PV plane leads to the isentropic process in the TS plane, right? So isentropic process, entropy constant. Again 3 to 4 temperature constant. So that means the TS plane is just a square. Yes. So if you this actually applies to apply on any cycles. There are some cycles we calculate in the PV plane in a more complicated way, but just switch into the TS plane and calculate and then come back to that. Okay. So this might be easy for some process you have to calculate. One, two, three, four. Similarly, if you calculate the auto cycles, in the PV plane, this is a Carnot cycle. Just replace the opposite. So yeah, so the or the volume constant, but in this case the volume constant is to this side, and entropy constant, that means 1, 2, 2, 3, 4. So 1 to 2 is a adiabatic. So in this case, it is a constant entropy. Just a reverse. So it's 1 to 2 entropy constant, 1 to 2 adiabatic process, entropy constant, isentropic process, adiabatic process goes to isentropic process, 2 to 3 is a volume constant, but in this case the volume constant leads to this types of curve. So this is a volume constant, isochoric process, and again isentropic process, and again isochoric process. So that means the TS plane, we just draw in the TS plane. This one. So isochoric, temperature constant, entropy constant, and isothermal. In this way. So it's the opposite to that things that we discussed. Yeah, this is that is for the PV plane. So but different isothermal, isothermal adiabatic in this case. So adiabatic is always more steeper than the isothermal in the PV plane. But what about in the TS plane? So this is a isothermal. Isentropic. And this process isochoric and adiabatic. Sorry, adiabatic, isochoric and isobaric. So in this case, that so in the apart from the PV plane, so PV plane that the isothermal and constant volume. So this is a isentropic, isochoric and isobaric are constant, but in this case they are. But in this case, in the so this is the opposite diagram. So this is So just replace this, right? So if you know that yeah, so if you just replace this what is the relations that dq equals to tds and so yeah, you have to plot this t versus s. Okay. So yeah, you have to derive that in this that isochoric process. How to define that? Explain that. Um, isochoric and isochoric. No, no, if the dq equals to tds, this thing you have to use, but you say that the pv equals to rt. T equals to pv by r. T equals to pv by r. So then the dq is pv by r. No, actually, they've got the volume constant. So, yeah, just a minute. Yeah, so then you calculate the slope dt by dx, right? At constant volume. It's 1 over r, and you have replaced the cv with r by gamma minus 1. This is actually gamma minus 1. The positives. Understand? Okay. So the thing is that so dt by ds is just a pv by r, right? So it's v by cv. So now is cv. This is replace this r by gamma minus 1. So v by r and gamma minus 1. And gamma is always greater than equals to 1. Right? So dt/ds slope is positive, right? So that's why the things is increased. Right? Yeah. No, no. Gamma is no, we are considering at one point dt ds, and no, there is a pressure also. No, sorry, there is a pressure also, right? So this thing and C by R. So CBT R by this one. So R square. There is pressure also, right? So that's pressure is changed. Right? If you say that no, that means that PV to the PV equals to RT, right? So if you say that the volume is constant, right? So now the temperature is increases. That means the pressure also increases, right? And that's why the slope is also increases. So that's why they are going this way, right? So well known means that the same way we have to draw the PV to the power gamma equals to constant, right? Hello. Hello, am I audible? Hello, am I audible? Hello, am I audible? Okay, I think there is some internet issue. Just a minute. Yeah, just a minute. Yeah, my screen is visible right now. No, at constant volume CPDT, at constant pressure for isobaric case is CPDT, right? Yeah, so which is greater? CP is greater or CP is greater? Oh, one minute, just a minute. So yeah, so then you ask this question for let's say for isobaric process. So isobaric process, this dq is CPDT, right? Then your relation that dTTS is that PV by CPR, right? PV CPR to DS. Sorry. So then CP is for ideal gas is greater than equals to CP. That means the slope which decreases rather than the isobaric process, right? Than the isobaric process. So that's why this isobaric process the slope is less to the with respect to the isomorphic cases. So understand this things. Yeah, so exact relations we just integrate, and so we also know that the DTDS, right, and just we integrate and we plot the graphs. So I am drawing the based on this slope DTDS. So you just integrate and we get relations with the T and S, right? There is a relations the T and S for isobaric process and isomorphic process. Okay, so I can write down these relations in the next sentence, but yeah, or maybe update in the lecture also. But there is a relation. At this moment, I'm not deriving this thing. I'll have updated in the lecture also. Just look into this and if you any point you can start. So that is that thing. So when we calculate the efficiency of these cycles, so it might be easy for some cycles in the TS diagram. So just convert it to the PP plane to TS plane and calculate the efficiency. Because efficiency is same. It does not depend on which plane are you calculating. So this will depend on the system parameters. So these are different. Okay, so then yeah, so one more thing we have to discuss that yeah, so for an irreversible change, so for an irreversible change, so for a reversible process, we say that this adiabatic process or for any reversible process, the entropy change is zero because this dq reversible by t, the closed line indicates zero for reversible process, the equality sign hold, right? So for a reversible process, so for reversible process, the delta is equals to zero. The change in entropy equals to zero. So what about the irreversible process? Irreversible process. So it's easy to see that this change in entropy delta is greater than equals to greater than not equal. So how do I know this thing? So let's do some on examples that let's say there is a unit and we connected one part, say reversible part, and another part we connect to this part. This is irreversible. And I calculate this dq by t is less than equals to for this closed path because this is not a reversible part. Some part of this reversible, some part of irreversible. So this closed path for this closed path is less than equals to because for any closed path any closed path, this relations must be whole. The equality sign only hold for reversible. So just we bring out this in two terms. So a to b dq. Okay. Just changing this. This is irreversible. And this is reversible. So a to b dq by t. I am putting card here because this is inexact differences. So as usual. Plus b to a dq irreversible by t. Sorry. B to a reversible. So we write for the reversible case the subscript that reversible, and when the process is irreversible, you cannot write. You are not writing. This is less than equals to 0. So now just we replace this that So now this is a B to A, we just a minus A to B. So dq by d less than equals to A to B. This one is clear. Okay. In this case, that B to A, so we just putting a minus sign A to B and then go to the right hand sides. Is this clear? So now we write this and ds. So this is ds is a state function that is defined for dq reversible by t. So this is the important that dq reversible. Only for the reversible process we define it. So that means it's greater than equals to, just write in the opposite way. It's greater than equals to dq by t for irreversible process. This is an infinitesimal change. Right? That's why we are not putting any integral a to b. So this is an infinitesimal change ds. It's all defined by the definition this dq reversible by t, and this inequality tells that this dq by t. So now that means that this ds delta s or any finite change is always greater than equals to 0 for any closed path. If the process is a reversible, then this equality equal 0, and if the process is irreversible, then greater than 0. No, it just why this relation tells that this is a greater than 0, that means for a thermally isolated system. Yeah. Yes. This does not depend on the, so this is a dq by t, which is state function. It cannot depends on the your path, but the process dependent. You calculate and get some value. But the ds only 0 for a closed path and reversible. This must be important. Reversible closed path, there is no change in entropy. Okay, but for an irreversible process, even if it closed, it's greater than 0. The change in entropy greater than 0. So we have calculated, let's say, A to B in an irreversible process. Sorry, in an irreversible process. Okay. So even this delta is greater than 0, right? So even in the closed path, but this is not 0. Only for the reversible path, this is 0. So that means in this case that why this is 0, that you just consider a thermally isolated system. Thermally isolated system, and in this case the thermally isolated system, that means that dq equals to 0. So then we can visualize this force. This is this is the statement of the another second law of thermodynamics. Another way to another statement of the second law of thermodynamics. Any change for the thermally isolated systems is always result in the entropy either staying in the same or increases. So for thermally isolated systems, the change in entropy same or increases. So when the same, for a reversible change, or irreversible process is always increases. Right? So if you consider any thermally isolated system, that means they are not connected with a heat reservoir or something like that. So the entropy is always increases for a irreversible processes, and for reversible process, the entropy must be same. Let's consider the mixing of the two gases and calculate the entropy. So, okay, so before going into this, we just consider some yeah. So we are consider some process. Let's go to the first law. What is the first law? That du is dq plus dw, right? So this du is a state function. It's a state function because this is does not depend on the path. But this dq and dw is not a state functions, and the sum of these two inexact differential becomes a exact differential. That is the example. So this is not a state functions, not a state function. That means they are not exact differences. They are path dependent, and du is a state functions. This is exact differentials and path independent. So for a reversible change, we write that things that for a reversible change, reversible change is dq is equals to tds, and this dw is equals to vdv. So or minus vdv according to the my sign conventions. So this equality only hold for reversible process. So this equality only hold for reversible process. So if we consider a irreversible process, right? So cannot think that for irreversible process, what is this relationship dq and this dx? What is this? Is equality hold or so go back to there. For irreversible change, dq by d and this ds. So that means that dq is less than equal to ds. Right? Right? What about dw? So dw is pdv, such that the du is dq plus dw is not changed. Is not change. Whether the change is reversible or is unchanged, that is the same. So it is same whether the change is reversible or irreversible. So these relations hold that TTS minus TTB. These relations always hold. So for irreversible process, dq dw in such a changes in such a way that this du must be same. And that is the internal energy. So when the internal energy changes, so one state function changes when the other state function changes, right? So it changes only the f changes or v changes, right? So one state function, so that's why you had write this is a extensive variables, right? When you calculate, you know that the extensive variable. So one extensive variable is depends on the other extensive variables, right? So that's why you write the ds. The change in extensive variable ds is related to dv and what are the other things? Is du. and what are the coefficients? I just say that from the here, right? So ds thinks that 1 over t du and minus p over t dv. Sorry, plus p. Yeah. So, or if you write that u, so thermodynamic, the mathematically, if you write that u is a functions of s and v, right? So if you write that du, it's del u derivative with the first variable del s, the volume is constant ds plus del u del v derivative partial derivative with respect to s dv. Right? This is the property of the partial differences. So then just compare with this. Okay? Just compare with this. That's equal and this is 2. Just compare with this. Compare 1 and 2. You get that p is del u del s v and t. And t is minus del u del s. So that means the ratio that p by t minus del u del v s and del s del u v. Just operate it. So we know that this p by t, what is this p by t? We have to write similarly, we have to write that s in terms of u and v, right? So this ds, again we have to write del s del u v du plus del s del v u dv. Now compare with this. So what about p by t? The p by t is nothing but the del s del v at constant u, right? So then this must be del s del v constant u. So that means this del s del v, sorry, del v del s at constant u, del s del u at constant v, del v yeah, del u del v at constant s, it must be minus 1. So this is again the property of the partial differences. So if u is a functions of s v, or s is a functions of u v and v is a functions of u s, this cyclic property, this is called the reciprocal yeah, so reciprocity theorem. It's a reciprocity theorem. So in this case we use that the reciprocal theorem means that we just replace that del u del v to del v del u. This is the reciprocal theorem. So this is used from this step, right? So from this step to this step we use a reciprocal theorem. Reciprocal theorem. So be crucial here. So that means that this del u del v, when we divided this p by t, this del u del v s, and we just replace the del s del u v. So this is the reciprocal. When we can do the partial, so if you familiar with the partial difference, that is the constant variable is the same, then we can just apply the reciprocal theorem. That means that del u del s at constant volume, right, is equals to 1 over del s. So just write down that del u del s at constant volume is equals to 1 over del s del u at constant volume. If we say that this is not equal, if this is, let's say, constant pressure, then this is not equal. So only for equal at constant, the same constant. So we are calculating this partial derivative with respect to the constant, let's say some constant x. So we have calculated del a del b in general some constant x. This is extended 1 over del b del a at same constant x. So we have used a different constant. This thing is not equal. So that is the reciprocal theorem. Okay. So this thing you have to know, and the reciprocity theorem is say that u is a function of f v. Similarly, I can write that from there that f is a function of u v, and also that the v is a function of f u. And reciprocity theorem tells that check the note that the cyclic structure del v del s del u del v. So when del v del s, the u is constant. When del s, so it's del s del s del s del u, v is constant, del u del v, s is constant. It gives a minus 1. So if you cannot apply the reciprocity theorem here, right? So you know that the del s del u and del u del v. So you can write a del s del, right? And then again, so that is the thing is that what is the important here, that so therefore I calculated del v del s at constant u, and we know that the del s del u and del u del v. So using this theorem, we just write this del s del v. Okay, and again del v del s del v, which is del v del v. It gives a 1. Right? The problem is that they are the three different constants are different. We cannot use the reciprocity theorem. That's why that gives a minus 1. Okay. So this is a big crucial here. Okay, so this is very important. The two relations. Okay. When they are equal, when we use reciprocity theorem and reciprocal theorems. It's clear, or in doubt? This minus 1 actually is the compensate from that. Okay, so say that the p by t it gives, and so when you match their definitions, is exactly the same. So this minus sign and this actually gives a del s del v. So this reciprocity theorem tells that this is del s del v, and this must be del s del v when we write down ds in terms of this. So this is one these two important relations, and it is in various process, or when you calculate thermodynamical potential. Thermodynamic potential, can you calculate very different quantities. So these two relations are helpful, very helpful. So next we calculate. Okay, so next we are going into the mixing of this two gases and calculate the change in entropy. So the mixing of entropy of mixing. Entropy of mixing. Again, so so let's say there is a two. Let's consider there are two vessels. One and another is denoted by 2. Okay? And we consider two different gas. So this is a gas 1, this is a gas 2. Gas 1, gas 2. And let's say the volume of this vessel is xv. xv is volume, percentage 1 minus x times. Now we connect. So total volume is such that the total volume equals to, so this percentage volume xb, this percentage 1 minus xb, and the total volume, when you connect, the total volume is 1. So then and the pressure and temperature is the same, right? So that means the number of moles are different. So your relation says that PV equals to NKP. So if you P and T are same, now the volume is different, right? So the number of moles are different also, right? So that means that we are mixing the number of molecules of gas 1 is Xn, mixing the Xn molecules, okay, this is Na, I forgot the number, or X mole, Xn molecules of gas 1 with 1 minus X in a number into molecules of gas 2. So this is important, there are two different gases. Let's consider. So can you calculate therefore the total number of molecules? Total number of molecules is n. So total number of molecules n, and the total volume is p. When we connect these two gases. So how do you think that entropy increases or decreases? How to calculate this? So what is the relations for, let's say, so now again say that the temperature is constant, right? So both the vessels have the same temperatures. Let's consider the isothermal expansions of an ideal gas. Right? So the isothermal expansion of an, let's consider the ideal gas. So both are ideal gas, but different kind of ideal gas. Let's isothermal expansions of an ideal gas. So internal energy du, but in the isothermal expansions, internal energy temperature does not change. For an ideal gas, this du is just only CVD, because U is only functions of temperature for an ideal gas. For real gas, U is a functions of both temperature and volume. But for ideal gas, it only depends on the temperature. So that means this is 0. Because for isothermal process, the dT is constant, so dT is 0, T is a constant. So that means the relation is TTS du equals to TDS minus PdV is equals to 0. So this gives that TDS equals to PdV. So what is your DS? P by D dV. Now use ideal gas equations. So P by D is just in kb and by P. Okay. So then we calculate and we know that the what is the changes in the volume for the this is the entropy mixing. So it's the delta is for gas 1. So for gas 1, this n, what is the number of molecules for gas 1? xna, xna, and the volume changes x v, total volume v, tv1 by v. So this is a integration variable, so I can change v to v1. And what about for gas 2? It's 1 minus x times na. The initial volume for gas 2, 1 minus x times v, and the final volume is v. Final volume is the total volume, right? So 1 minus x times v would be, and let's the integration variable dv2 by v2. So if we calculate this, is the total delta is the delta s1, delta s2. Okay. So s is an extensive variable, right? So that's why we add for the gas 1 the change in entropy and the gas 2 in the change of entropy is additive. So entropy is always additive. So the total delta is total, just the adding of the two systems, gas 1 and gas 2, changing into gas 1 plus the changing into gas 2. Is the entropy is additive property. So it implies that yeah, KB, Boltzmann constants. Now we do the integrate and do this integrate, we get the result that minus NAKB times x ln x plus 1 minus x ln 1 minus x. So now we plot this. What is the XL limit? Let's say plot delta is total over what is the limit of x? Remember that s is a fraction of the total volume, right? So it's always 0 to 1. That's why. So you say that the delta is total. Delta is total is a negative. But this x is the limit is that x is at 0 to 1. So that means this ln some 1 over something, it gives a negative. The total is greater than equal to 0. So that means if we plot this delta is total by NAKB, so that's x equals to 0, 0, and increases at some point and then again at x equals to 1. So at some point is maximum. And this is actually is point that x equals to half. Half is the maximum. Now what is the maximum value? So calculate the so for x equals to 0, delta s total is 0. X equals to 1, delta s total is 0. For x equals to half, okay, delta s total. Just calculate and let's say half and this half and half. 1 minus half is also half. So it's 2 in kb. Yes, right, right. So that means that this is a corresponding to the equilibrium state in which no further increase in entropy is possible. Yes, element peak value is element. So now what is happens actually. So so what is the statistical interfaces? So we have think the statistical interfaces. So that means that before the mixing of the gases, so we know that the gas one is so vessel one is only contains the gas one, okay, and vessel two it only contains the gas two. So after mixing, we cannot tell that which molecule is a gas one type or gas two types. Right? So there is a probability that it might be a gas one molecules or might be a gas two molecules. Right? So that's why this two possibilities and so if we calculate the phi, it's the number of microstates. So when we go into the statistical mechanics of the number of microstates, it becomes more clear. It's actually 2 to the power n. There is any molecules, and each molecules there is a two possibility. That's why two. And for any molecules, the same thing happens. So the number of microstates to multiply. So the 2 to the power n, and we just calculate this if it's kb ln psi. This is the Boltzmann formula. So we just put into there, we can get it to sorry, na ln. The same thing. So that is the case for the for x equals to half case. Because for x equals to half means that both are the same amount of molecules. Only for the x equals to half. Be crucial. For x equals to half, because that the gas one molecules and gas two molecules are same, right? Initially, and when you mixing, there is a if we there is some mismatch. Let's say the 1/3 of molecule gas one and 2/3 of molecule gas two. Then this is not a the each molecules. This is not a probability. Uh, the same probability for a gas one and gas two, because there is some there is a initially density difference of these two molecules. So it's only true for if x equals to half, and this gives these results. And you calculate in the above prescriptions, and you get the same results. That is the importance. Okay, so then just go into the assignment problems. Okay, I think most of the problems we already discussed. Just, it's already time over. Just quickly go through this. Yeah, so you know how to calculate the change in entropy for a real gas. So yeah, so one more thing that the dq. So you have to calculate that the dq is the in general is that CVDT plus you know the other relation is that d del p del t v dv minus dt. So I derived this relations in the previous I think in some classes I derived this relations. So just go back and check this, and we just put into this formula because this is true for any gas. So this is true for this relation is true for in general, in relations in general for any cases, ideal or real, whatever. So just to calculate this del P del V and PdV. So for ideal gas, we say that for ideal gas, just quick check. For ideal gas, we calculate this T del P del TV you get a P. And this relationship is dQH. Just simulate it. But for real gas this is not true. This is in general, and you know that the dq how to relate the TDS and then calculate the entropy. And then the entropy mixing calculated. Other process of the cyclic process calculate the efficiency. You know how to calculate the efficiency. Yeah. So one more problems is the time. Let's take 4 minutes. It's okay. Okay. So I just discuss one more problems. So question is that let's say two identical body have the same heat capacity. Identical body have same heat capacity C and the mass is same. Mass is same, the same mass. So initial temperature is T1, T2. Let's draw the diagram that let's say this body 1, T1, the heat capacity C and the heat connected to another body it's T2 and the same heat capacity and mass. So now they are used as a source of, so there is a temperature difference T1, T2. So now we can use as a source of heat engines. So let's say they are so because of their temperature differences of the two bodies, we can use they are used as a source of work by connecting them to a let's say canode engine. More specifics, we can use any kind of heat engine, but here we use canode engine, and bringing them to a common final temperature Tf. Tf. Right? So then we can replace this kind of thing. So take canode engine C and deliver some. So question is that let's say first question one that what is the Tf? What is the Tf? The second question is that what is the work delivered? Okay. So first of all, when we connect two body at different temperatures, what is the final temperatures? Not there is not any engines, right? So let's say the two body just connect with a say T1 and T2. There is no engines. So what is the final temperatures? Means that in thermal, so there is a thermal equilibrium, a common temperature, right? So what is the final temperatures? Let's say the heat capacity C the same. Yeah. So T1 plus T2, right? So if the masses are all C1 and C2 are not same, then we can just C1 and C2 and then C1 plus C2, right? So I also derived these relations in the previous some classes. So go into the details and then go through this. So now we are insert engines between them. and we are calculating the final temperatures. So when we insert, that means we know that for a Carnot engine, so for a Carnot engine, you know that this dq reversible by t is equals to j. That means the dq1 over t1, okay, plus, so I use this convention that both are plus sign, dq over t2 equals to 0. So now what you are dq1? dq1 is mc, same thing dt1, the change in the temperature, and whatever the dq2 minus mc dt2. Right? So I put a minus sign here. Okay. So then I will just put a t1 to tf is dq1, put this dt1 over t1 is equals to minus tf to t2 dt2 over t2. So sorry, in this plus, so this is t2 to tf, this is a plus, then this minus and minus and compensate. So then we can calculate this, because t2 is greater than t1 and tf is the medium. Sorry, still not consider this thing. We have just calculated this. So then we can calculate this ln tf by t1 minus ln tf by t2. One minute. So t2 by tf dt2. So this tf is actually square root of t1. This thing is clear now. For a cyclic process, so t1 to tf and tf to t2. So you will replace this limit, so it gives a minus sign, and yeah, just go through this. And then so this is the final temperature, right? It's square root of t1 and t2. Now the second thing that calculate the work done. So total work done is just the conservations of energy tells that this just this q2 minus q1. If you know this q1 and q2, what about your q2? Just mc minus tf minus t2 minus mc tf minus t1. This is just mc t1 t2 minus t2. This just comes from the conjunctions of energy. Yeah. Yes. I just yeah. What do you say that entropy change? This is a reversible process, right? So we consider Carnot engine. There is two specifics the Carnot engine. If we consider any other kind of engines, then we consider. And this thing is not applied for any other kind of engine, right? For irreversible engine. For any other reversible engine, you can also apply this thing. So that's why I'm saying that DQ reversible by T. And in the question I also written that this is a Carnot engine. So this is very specific. Okay. Okay. So let me stop here and we'll meet on the next week. Yeah, I'll tell this thing to my instructor. Yeah. Okay, bye bye.